Hi everyone, welcome to the Cosmic Space Channel. Tonight, we'll journey through the deepest mysteries of the universe. If you're ready, let's begin. There are two numbers, 67 and 73. Both are measurements of the very same thing. They're both attempts to answer one question: how fast is the universe expanding right now, tonight? Two separate teams, using the most precise instruments humanity has ever built, arrived at these values. Under normal circumstances, they should agree. They don't. And here is the part that should give you pause. As our measurements have gotten better, these two numbers haven't moved closer together. They've drifted further apart. The Big Bang is widely considered one of the most successful theories in the history of science. It predicts the temperature of the infant universe with an error of less than 1 part in 1,000. And yet, the closer we examine it, its own expansion, its explanation for 95% of everything that exists, and its account of the very first moment, the more its inconsistencies come into focus. So what's actually happening? Why does our strongest theory grow less sensible the more carefully we look at it? Relax for a moment. Tonight, by the end of this, you'll understand exactly what it means for a theory this successful to begin fraying at the edges, and what that might mean for the future of physics itself. Let's ease slowly into the first part. I want to start with something that will make everything else in this story feel even stranger. The theory we're about to gently take apart, the one that keeps drifting out of focus the closer we look, is not a bad theory. It isn't some fragile, shaky structure. By almost every measure, it is the single most successful explanation of the universe that human history has ever produced. So before we get anywhere near the cracks, I want you to feel just how solid the ground really is. Because everything strange we're about to explore tonight rests on this same foundation. The core idea can be summarized in a single sentence. The universe was once hot, dense, and far smaller than it is now. Over roughly 13.8 billion years, it expanded and cooled into the cold, quiet emptiness we live in today. That's the Big Bang. Not an explosion, not a scream. We'll come back to that idea later. Just a process, a universe that was once small and hot, and then grew and cooled. From this simple idea, physicists built a model. They gave it a fairly clunky name. Lambda-CDM, the cosmological constant, plus cold dark matter. We'll meet both of these ingredients again tonight, because both of them cause trouble. Here's the crucial thing to understand about this model. It rests on just 6 numbers. 6 measured values, pulled from the sky, fed into the equations, and from those 6 numbers, the model reproduces almost everything we observe with startling accuracy. It predicts the universe's rate of expansion. It determines how the lightest chemical elements, hydrogen, helium, and a trace of lithium, formed in the very first minutes, long before any star was born. And most impressively, it predicts the fine pattern of warmth and cold across the oldest light in the sky, the cosmic microwave background, matching it to an accuracy of better than 1 part in 1,000. Pause for a moment and consider what that means. A theory built from just 6 numbers tells you what the temperature of the entire sky should have looked like when the universe was younger than 400,000 years old. And when you point a satellite at that sky, it confirms those numbers, decimal place by decimal place. This isn't luck. It isn't a guess. It's one of the greatest intellectual triumphs in human history. No serious scientist anywhere in the world doubts the core of this result. The fact that the universe really was hot and dense, and has been expanding ever since, is considered about as certain as the fact that the Earth orbits the Sun. Let's add a little more detail. The scale of this success reaches back to just the first few minutes after the beginning. In those moments, the entire universe was hotter than the core of any star, and under those conditions, the lightest atomic nuclei formed. Theoretical models predict that this early cooking process should leave the universe made of roughly 75% hydrogen and 25% helium by mass, with only a faint trace of other light elements. When we measure the oldest, purest clouds of gas we can find, gas that has never passed through the inside of a star, nearly untouched primordial material, the observations match this prediction almost exactly. The ratio of hydrogen to helium comes out close to 3:1, agreeing with the prediction to within about 12%. The theory looked back to the first 3 minutes of time and said what elements should exist, and the universe agreed. The cosmic microwave background does more than confirm this harmony. It carries a far more remarkable feature. The pattern of warm and cool spots forms a series of peaks in a specific order, almost like a cosmic musical note. The exact height of these peaks encodes how much normal matter and how much dark matter existed in the universe's earliest moments. Physicists predicted the shapes of these peaks before the best measurements ever arrived. When the measurements came in, the peaks appeared exactly where the theory said they would. The third peak in particular is essentially a direct fingerprint of dark matter, stamped into light nearly 14 billion years old. When a theory makes a prediction this specific, this far in advance, and the universe delivers on it, that earns deep trust. This isn't a house of cards. It's built more like a cathedral. Which is why, when cracks do begin to appear, the unease they cause feels less like a crack in a garden shed, and more like a crack in a cathedral's arches. Hold on to that feeling. The sense of standing on solid ground, while somehow also sensing that the ground has begun to shift, ever so slightly, beneath you. That's the quiet paradox hiding inside this whole story. Over the last 15 years, and especially since around 2019, something odd has been noticed in this remarkably successful theory. Our instruments have grown sharper. Our telescopes have grown larger. Our observations have grown deeper, our measurements more precise. And as they have, the theory hasn't grown more comfortable. It's grown more uneasy. The numbers have started to disagree with each other. This disagreement has produced two different answers to what may be the single most fundamental parameter in all of cosmology: how fast the universe is expanding right now. Depending on which method you use to measure it, the two values diverge, and the gap between them has become something physicists openly call a crisis. 95% of everything that makes up the universe remains two mysterious substances we've still never directly detected, understood only through their gravitational effects. And in just the past few years, the largest map of the universe ever built has begun to whisper that something we assumed was a fixed, unchanging property of empty space might actually be changing over time. This is the paradox itself. The Big Bang fits the data better than almost any theory ever proposed by anyone. And yet the closer we look at it, the less internally consistent it becomes. The sharper our eyes get, the stranger the view. Tonight, we're going to examine that strangeness slowly, piece by piece, like tracing a hairline fracture, and try to work out what it ultimately means. Because the answer we'll arrive at is very different from what most people assume. It's quieter, stranger, and, in a way, more hopeful than either the people who claim the Big Bang is a lie, or the people who insist it's finished and flawless. So settle in. Our journey won't begin with a crack. It will begin with the deepest fracture of all, one hidden right at the very beginning of everything. This crack marks the exact moment the theory's own name was born. Right at the instant of the Big Bang itself, a problem appears that the theory cannot solve on its own. Imagine the entire history of the universe as a film, and imagine we're going to run that film backward. The scene we're watching right now, tonight, is what we see: galaxies scattered through darkness, slowly drifting apart from one another. The whole universe slowly expanding, slowly cooling. Now let's rewind the film. As we move backward, the galaxies begin to drift toward each other. The space between them shrinks. The universe shrinks. And whenever you compress a universe, you're forced to heat it. So the universe grows hotter and hotter as the film keeps rewinding. The galaxies dissolve into shapeless, glowing gas. The gas grows denser, brighter, until the entire cosmos becomes a single, uniform source of white light, a sea of particles hotter than the core of any star. It becomes so thick that not even light can pass through this haze of pure radiation. Rewind further still, and the seconds compress. We pass the moment the first atomic nuclei formed. We reach the universe's very first second, when it was a boiling soup of fundamental particles. The temperature exceeds anything matter as we know it could withstand. But as long as Einstein's equations of general relativity keep pointing the way, the story keeps getting smaller and hotter and smaller and hotter right up to the final frame. And in that final frame, the film breaks apart. When you reach the moment we call the beginning, the mathematics doesn't hand you a very small, very hot universe. Instead, it hands you something that isn't a physical answer at all. Zero size, infinite density, infinite temperature, infinite curvature in the fabric of space-time itself. Every quantity that's supposed to be a number simply runs off toward infinity. Physicists have a name for this. It's called a singularity. A singularity isn't an object. It isn't a place. It's the sound a theory makes when it breaks. In physics, infinity is rarely a real, measurable value in the world. When your equations hand you an infinity, they aren't describing something that's actually infinite. They're telling you, in the only language they have, that they've simply stopped working. It's the mathematical equivalent of dividing by zero. Your calculator won't give you a real answer for 1 divided by 0. You get an error because the question itself has stepped outside the boundaries the arithmetic can handle. That's exactly what general relativity does at the first instant of time. It throws an error. The very theory that describes the universe so beautifully, so precisely, cannot describe the 1 minute it's named after. Let's sit with this strangeness for a moment, because it's easy to move past it too quickly. We have a theory that explains the origin of everything, and yet that theory cannot describe its own origin. The map of the universe has a hole in it, and that hole sits exactly where the story is supposed to begin. You might reasonably ask, is this just a coincidence? Maybe with cleaner equations, or better assumptions, this singularity could be smoothed away. But the situation doesn't get better here. It gets worse. In the 1960s, Roger Penrose and Stephen Hawking, working from fairly mild, reasonable assumptions about general relativity and the behavior of matter, produced a series of theorems and mathematical proofs showing that this singularity in our cosmic past is, in a fundamental sense, unavoidable. This isn't a setup error. It isn't something a cleverer model could patch over. It's a feature built into the theory itself. If general relativity is taken to be true all the way back, then the beginning has to be the place where general relativity fails. When the theory reaches its logical conclusion, it proves its own breaking point. It's worth pausing to consider how unusual this is. Most theories don't gently announce their own limits. They quietly give wrong answers, and it's left to us to notice the mistake. General relativity does something rarer and more honest. Its own mathematics shows you exactly where its reliability runs out. Instead of leaving an empty gap at the edge of known territory, it's almost as if the map itself prints a warning right at its border, beyond this line, this map means nothing. That's a strange, almost noble thing for a theory to do. Alongside its success, it hands you a warning label. There's a subtle point here worth catching, and I want to state it clearly. The singularity is probably not literally a real physical thing that happened. Most physicists don't actually believe a moment of truly infinite density ever occurred. The singularity is a sign that our description has run out, that the real physics of that moment is governed by rules we simply don't have yet. Think of it this way. Sailing across the sea using a flat map of the world, the map might present you with an impossible edge or infinite weirdness. But in reality, no such boundary exists. You've simply reached the North Pole, an ordinary place where that particular flat map breaks down. The infinity is in the map, not in the world. The singularity at the beginning of time may be exactly this kind of illusion. A point where our physics map tears, while the actual territory remains smooth, orderly, and just beyond our current field of view. The trouble is, we still don't have the globe in our hands. We only have a torn map, and the tear sits right where the story is supposed to begin. So what was inside that first moment? The honest answer is that we don't know yet, and we can't currently know. Answering this question with our existing physics requires a theory that unites general relativity, which governs the largest scales of the universe, with quantum mechanics, which governs the smallest. At the singularity, the entire cosmos is simultaneously indescribably heavy and indescribably small. Two separate rule sets are meant to apply at once. But right now, we don't have a theory of quantum gravity that can handle that. There are candidate ideas that might fill this gap. Some propose that the singularity is replaced not by an infinite point, but by a bounce, or a gentle, finite transition. But these proposals remain unconfirmed, more like margin notes on a page we still can't read. Seeing how different these various drafts are from one another actually shows just how open this question remains. In one approach, called bounce cosmology, the universe never truly had a beginning at all. A pre-existing universe was collapsing inward, growing denser and hotter, and just before reaching the singularity, quantum effects halted the collapse and pushed matter back outward in a bounce. In this view, the Big Bang is actually the big bounce of an earlier cosmos, and time extends backward through that event into an entire prehistory. In another line of thinking, the beginning is described as a rounded shape with no sharp edge at all. The surface of a sphere is finite, yet has no edge. In this framing, the question of what came before the beginning becomes as meaningless as asking what lies north of the North Pole. In yet another approach, our universe is a single bubble that formed within a constantly inflating background. The birth of that bubble is the beginning of our universe, and an infinite landscape stretching in every direction contains other universes as well. These aren't idle daydreams. They are serious mathematical proposals developed by working physicists. What's interesting is that they can't all be true at once, and yet each one remains compatible with everything we currently observe. That's the honest truth of it. We have several radically different possible stories about the origin of the universe, and we haven't yet been able to determine which, if any, is the real one. This reshapes a phrase we repeat often. Our work on the Big Bang doesn't just deepen the complexity of the question. It also reveals that, at the level of the very beginning, we don't even have a single verified story. We have a shelf of competing narratives, and a gap where the evidence should be. The origin of the cosmos isn't a loose end waiting to be tied off. It's a wide-open boundary, and every layer of knowledge we've built rests on top of that openness. This is where the human weight of it settles in. When someone asks what exploded in the Big Bang, or what existed before it, the most honest answer is that the theory simply doesn't contain that moment. In the popular telling, the beginning is exactly where our best theory goes dark. We haven't lost the opening scene. It's that, in this reality, it never actually existed for us to have. So, well before any new discovery from a modern telescope even touches this, there is already a void sitting at the very center of the Big Bang, and this remains, even now, a new kind of beginning. The problem isn't only a gap in the theory. It's that this is a subject almost everyone assumes they understand, and most people are, in fact, deeply mistaken about it. When people hear the words Big Bang, there's an image that almost everyone carries in their mind. A glowing point, alone, surrounded by nothingness, suddenly erupting outward in a cosmic explosion, filling the surrounding emptiness with stars and galaxies. It's a vivid, dramatic image. And it's wrong in nearly every meaningful detail. Let's gently take this apart, piece by piece, because getting this right makes the difference between understanding the rest of tonight and staying lost in it. First, the Big Bang was not an explosion happening inside space. It was the expansion of space itself. This is a genuinely difficult idea. Let's use the analogy physicists use. Picture the surface of a balloon, with dots drawn on it in pen. Each dot represents a galaxy. Now inflate the balloon. Every dot moves away from every other dot, not because the dots are sliding across the rubber, but because the rubber itself is stretching, carrying the dots along with it. The expansion has no center. There's no special dot that all the others are rushing away from. Every dot observes every other dot moving away from it. The expansion happens everywhere in space, all at once, uniformly. That's exactly what the universe is doing. Galaxies aren't flying through space away from some central explosion. Space itself is expanding, and galaxies are carried along with that expansion, the way dots are carried along the surface of an inflating balloon. That's why the question, where did the Big Bang happen, has no answer. It didn't happen at a point. It happened everywhere. The place where the Big Bang happened is right where you're sitting now, and it's also the most distant galaxy we can see, and every point in between. There is no center, because there's no outside from which to measure one. Second, and this connects directly to the first point, there is no edge and no outside. The universe is not a sphere of galaxies expanding inside some larger empty room. As far as we know, the room itself doesn't exist. The expansion isn't the universe growing into a pre-existing emptiness. It's the emptiness, space itself, that is growing. There is nothing outside for it to grow into. This idea can feel strange to hold in your mind. Take your time with it. The expansion doesn't happen within space. It happens to space itself. Third, and finally, connected to everything before it, the standard Big Bang model doesn't actually describe that very first moment. It only describes what came after. The story begins already in progress, at a fraction of a second into a universe that's already hot and dense, and from that point onward, the model proceeds with tremendous accuracy. But at the mathematical point of zero size and infinite density, the singularity we've been sitting inside this whole time, the theory simply cannot capture that instant. So when we say Big Bang, what the term actually describes isn't a moment of creation. It's the continuation of an event we can't directly observe, picking up right after a beginning that remains hidden from us. Now let me tell you where this name came from, because it's a small historical detail that has quietly misled people for 70 years, and it's almost comical. In the mid-20th century, there was a genuine scientific debate about the origin of the universe. On one side were the people arguing that the universe had a hot, dense beginning. On the other was an astronomer named Fred Hoyle. Sharp, stubborn, and brilliant, Hoyle argued that the universe had always existed, with no beginning at all. Hoyle thought the idea of a sudden origin was almost laughable. In 1949, giving a talk on BBC Radio, he wanted to describe this idea dismissively, and he mockingly called it the Big Bang. The phrase was meant as an insult, a jab. But the name stuck. Today, every child who hears this term pictures exactly the crude explosion Hoyle was mocking. The theory itself is telling us that this striking image is wrong. The most famous name in cosmology was coined, as a put-down, by the theory's biggest opponent, and it's been shaping how the public imagines the universe ever since. There's a small, worth-savoring irony here. By any measure, Hoyle was a great scientist. He did foundational work on how elements heavier than helium are forged inside stars, work that underpins much of modern astrophysics. His one real mistake was being wrong about the origin of the universe, and that mistake left him with the most lasting brand attached to the side that won. The man who thought the universe never began is the one who gave us the name we use for its beginning. Those two dismissive words, chosen in mockery, planted a wrong image in people's minds before any real explanation ever had the chance to. I bring this up because language shapes intuition far more than we tend to think. A bad name is a quiet, persistent form of misinformation. If the theory had instead been called something like the Great Expansion, or the Everywhere Stretching, generations of people would carry a more accurate picture. There would be no room for the question of where the expansion happened, because expansion doesn't happen in a location. There would be no image of an edge, an outside, or debris flying through darkness. A great deal of the confusion we've untangled so far traces back to a phrase improvised as a joke over the radio waves in 1949. So for the rest of tonight, as we look at the places where the Big Bang seems to stop making sense, hold on to one thing. Some of that senselessness never existed in the universe at all. It was baked into the words we chose. But not all of it. As you'll see, much of it is real, and it's written directly into the sky itself. I mention this not as a mere aside, but because it serves a deeper purpose. When people, and an increasing number of them, say the Big Bang is starting to make less and less sense, it matters to understand exactly which part they mean, and which part they don't. They usually aren't talking about the foundational claim that the universe was once hot and dense, and is now expanding. That claim is a steady rock. It isn't in danger. The trouble appears in the full, detailed version, the version that tries to explain every number, every ingredient, every last detail of how the universe evolved from the hot, dense state into what we see today. It's this detailed version that keeps failing its own tests. Now that we know which part is solid and which part trembles, we can look closely at the trembling part. The first step is to look at a piece of sky that agrees with itself for no obvious reason. Picture a scene where the sky agrees with itself with no logical justification. I want to show you two of the farthest points we can observe, and describe a fact about them that shouldn't, by nature, be possible. Point a telescope toward one edge of the observable universe, as far as light has been able to travel to reach us, roughly 13 billion light-years away. Notice the faint glow of the early universe there, and record its temperature. Now rotate the telescope a full 180 degrees, and look at the exact opposite edge of the observable universe, an equally immense distance in the other direction. Measure the temperature of that region too. The two measurements aren't just similar. They match to within 1 part in 100,000. If you compare the temperatures of these two utterly separate patches of sky, you'll find agreement out to 5 decimal places. So why is this actually a problem, and why has it kept cosmologists awake for decades? These two regions of the sky have never, at any point in the universe's history, been able to make contact with each other. Light is the fastest thing in the universe, setting the absolute speed limit for any signal or any transfer of energy. But light has never had time to travel between these two regions. In the language of physics, each point lies outside the other's horizon. The farthest either one could ever reach, even at the speed of light, doesn't cover the distance to the other, not even accounting for the entire span of time since the beginning. Now think about what it would actually take for two objects to reach the same temperature. A hot cup of coffee sitting in a cold room exchanges heat with its surroundings and eventually reaches equilibrium. Two regions can only trade energy and equalize their temperatures if they're able to communicate in some way. But these two patches of sky have never had that kind of contact. Not a single photon has ever been exchanged between them. In the standard cosmic model, there is no mechanism that would let these two regions arrive at the same temperature. And yet, in every direction, at every point, these regions display the exact same temperature with staggering precision. It's as though two people who have never met, never been in the same room, independently chose to wear the exact same outfit, down to the exact same shade of color. You might be tempted to call that luck. But there's a more honest reaction. Something must be binding these together, and it isn't visible to us. That's precisely the position cosmologists find themselves in. The universe being this uniform, this smooth, this consistent, directly contradicts the fact that no communication mechanism in the theory could have produced that agreement. A crowd of strangers who've never met independently choosing the exact same precise shade of color isn't something you can wave away as coincidence. It's a phenomenon that resists easy explanation. So the uniformity of the universe isn't a comfort. It's a puzzle. A smooth cosmic structure is, in fact, far harder to explain than a random, patchy one, because smoothness implies communication, and communication, here, is impossible. It's worth grounding this impossibility in something concrete, because it's the very heart of the problem. Light sets the ultimate speed limit. Nothing can exceed it. That basic fact is exactly why the temperature match between these two distant patches of sky forms a genuine paradox. Nothing, no signal, no wave, no influence, can travel faster than light. So the farthest any influence could have reached since the beginning is defined by how far light could have traveled in that time. That distance defines a boundary around every point, what we call its horizon. Nothing has ever been able to reach beyond that shell. If you work through the mathematics of the early universe, you find that at the moment the cosmic microwave background was released, each region of the sky had its own horizon, far smaller than the sky we observe today. The universe we see now is built from countless numbers of these tiny fragments, each one, at that early time, completely isolated from all the others. Distant regions weren't within each other's horizons. No heat transfer ever occurred between them. By the rules we understand, These regions should have cooled down to whatever random temperatures they happen to land on, and the sky should be a chaotic patchwork of random temperature differences. But observation shows the opposite. The universe is extraordinarily smooth and uniform. This leaves cosmologists with a genuine dilemma. Either countless causally disconnected regions arrived at the exact same temperature by pure chance, which makes no sense, or something happened very early on, something we haven't yet accounted for, that allowed these regions to communicate once, or share a common origin before they were ever separated. This uniformity isn't a minor detail to set aside. It's a cry for a new physical explanation. And the flatness problem, sitting right alongside it, raises that cry even louder. When we measure the large-scale geometry of the universe, we're trying to determine whether space curves like the surface of a sphere, curves the opposite way like a saddle, or is simply flat. The result shows that the universe is, to an almost perfect degree, flat. This is a miracle in its own right, because flatness is an unstable condition. Even the slightest curvature in the early universe would have grown into something enormous over billions of years, the way a tiny error at the start of a long journey lands you in a completely different country by the end. For the universe to display the near-perfect flatness we observe today, it must have started out flat to within an accuracy of about 1 part in 10 to the 62nd power. That's a 1 followed by 62 zeros. This kind of fine-tuning isn't something anyone can casually explain away. So the universe is both extraordinarily smooth and extraordinarily flat, and the basic Big Bang model, on its own, cannot explain the reason for either. These aren't small oversights. They're enormous inconsistencies shining right on the surface of everything we observe, and the existing theory, by itself, cannot account for them. Physicists discovered a single possibility that could solve both problems at once. The solution is both elegant and beautiful, and it's become part of the standard cosmological narrative. But here's where things get more complicated. This finding involves one of the strangest and most contested ideas in the history of physics. In resolving the mystery of a smooth, flat universe, we may have traded it for a deeper mystery still. The idea is that the universe underwent a period of inflation in its very first moments. Inflation predicts that in an extraordinarily brief window of time, somewhere between 10 to the -36th and 10 to the -32nd seconds, the universe expanded by an unbelievable factor. This process would have taken the tiny, isolated regions we described earlier and pulled them together, letting them share the same temperature conditions before ever separating, which explains the uniformity we observe in the cosmic microwave background. At the same time, inflation flattens the universe's geometric curvature. The rate of expansion rapidly irons out any early curvature, driving the universe toward near-perfect flatness. The fact that a single mechanism can solve both problems at once is what makes inflation so appealing. but the idea of inflation has its critics as well as its defenders. What field actually supplies inflation's energy, how that energy comes to an end, and how it integrates with the rest of particle physics, all of this remains uncertain. What's more, the cosmic texture that forms after inflation, things like cosmic strings, and the possibility of a multiverse, offer a speculative framework that reaches beyond the standard model. For this reason, the true explanation behind the universe's smooth, flat structure remains a genuine open question. So, cosmological observations show that the universe displays remarkable uniformity and flatness, and the one process proposed to explain both at once, inflation, has raised new questions and new theoretical debates of its own. Deep uncertainty about the universe's origin persists. In the next part, we'll look at how inflation itself became a mystery, and how that mystery came about. In the late 1970s and early 1980s, a young physicist named Alan Guth was wrestling with exactly the problems we've just described. The universe's smoothness, its flatness, and the missing exotic particles that should have appeared in the early universe but never have, these three problems were pressing on him at once. He arrived at a powerful idea that solved all three problems in a single stroke. It's called inflation. Here's how the idea unfolds. In an unimaginably brief slice of the universe's existence, less than a billionth of a billionth of a billionth of a second, the universe underwent a burst of expansion so extreme that trying to express the growth rate in numbers becomes almost meaningless. A region smaller than the width of a proton, in that unthinkably brief instant, stretched out to a size exceeding the entire observable universe we can see today. So how does this solve our problems? Let's take them one at a time. The smoothness problem. Before inflation, the entire observable universe was a single, extremely small region, small enough for heat to flow freely between its parts and reach a common temperature. Inflation then took that already uniform patch and stretched it out to cosmic scales, while preserving that same uniformity. The two opposite edges of the sky look consistent with each other because, before inflation, those edges were close enough, near enough, to essentially be in contact. Inflation carried them to enormous distances apart, without erasing the agreement they'd already reached. The flatness problem follows the same principle. Stretch any curved surface by a large enough factor, and it will appear flat. The same way the ground beneath your feet looks flat simply because the Earth is so much larger than you are. Inflation stretched the universe so dramatically that it became, for all practical purposes, flat. The third and strangest problem was the missing exotic particles. Some theories predict that in a very hot early universe, huge numbers of heavy, stable point particles called magnetic monopoles should have been produced. But to this day, not a single monopole has ever been observed. Inflation explains this absence naturally. If these monopoles were produced before the period of expansion, the enormous stretching that followed would have diluted them so thoroughly that only a tiny handful might remain anywhere in the observable universe, far too few for us to ever have caught one. This single idea hasn't lost its appeal, because it solves three deep problems at once: the horizon problem, the flatness problem, and the missing particle problem, all vanish together. And inflation's predictions about tiny fluctuations in the early universe have since been confirmed by later observations. For all these reasons, inflation has become part of the standard cosmological model, widely taught and widely accepted. On the surface, this looks like a triumph, the rise of physics right in the midst of a crisis. But now let's turn this idea over and look at the weaknesses underneath it, because that's exactly where the problem begins. First, what actually triggered inflation remains a mystery. This enormous burst of expansion requires something to have driven it, some field or form of energy filling the early universe, with very particular properties. Physicists gave this hypothetical entity a name, the inflaton. But naming something isn't the same as discovering it. This field has never been observed. We don't know what it is, where it came from, or exactly how it acquired the properties needed for inflation to work. The very mechanism claimed to solve the mystery is, itself, entirely unexplained. Second, something even stranger emerges. In many versions of the theory, inflation doesn't cleanly end. Once triggered, quantum effects can keep it going. It ends in some regions while continuing in others. This means that, throughout the whole of reality, inflation may never actually stop everywhere. In an endless cycle, one pocket after another, one bubble after another, keeps forming, each one likely representing a separate universe with potentially different properties. This is called eternal inflation, and it points not to a single universe, but to a multiverse of endlessly proliferating universes. So the entire cosmos we can observe becomes just one bubble among an infinite number. The very theory we use to explain a smooth, uniform universe leads us toward predicting countless other universes we can never observe. The third and most striking criticism comes from within the field itself. Paul Steinhardt, one of the original architects of inflation, became not only one of its builders but one of its sharpest critics. Making an argument that's disarming in its simplicity, Steinhardt points out that inflation, in its full form, is flexible enough to be tuned to produce almost any outcome you want. Different versions, different initial conditions, different values for the mysterious field. With these combinations, you can arrive at nearly any set of universe properties. But Steinhardt argues that a theory capable of predicting everything actually predicts nothing. If every possible observation is compatible with some version of inflation, then no observation can ever truly test the theory, and a claim that, in principle, can never be proven false creates real discomfort even within the boundaries of science. So let's take stock of where we are. We brought in inflation to explain why the universe is smooth and flat. But inflation still requires an undiscovered, unidentified field. That field may give rise to infinitely many universes we can never observe. And one of the people who helped build the theory argues it might be entirely unfalsifiable. So rather than solving the mystery, we may have relocated it, and perhaps deepened it. This patch conceals a hole of its own. Still, I want to be fair to inflation, because it would be easy, but not accurate, to dismiss it as a mere hand wave. Inflation made a prediction, and that prediction turned out to be startlingly correct. The theory predicts that the same violent expansion that smooths and flattens the universe should also stretch the tiniest microscopic quantum jitters, ones required by quantum mechanics throughout all of space, up to cosmic scale. These stretched jitters become slight variations in the density of the early universe. A little denser here, a little sparser there. These variations leave a specific, calculable pattern in the cosmic microwave background, and later act as the seeds around which galaxies eventually form. When we map the microwave sky in detail, that pattern is there, and it matches inflation's prediction remarkably well. So inflation isn't just a story. It carries a genuine observational triumph, and that's why many cosmologists continue to take it seriously, despite its problems. But here's the truly frustrating part, the part that keeps the whole subject honest, that keeps the search for answers alive. That same success can't be credited to a single specific inflation model. It applies just as well to many different variants of inflation, and even to some of its rivals. A prediction that works doesn't, by itself, single out one specific theory. This leaves us in an uncomfortable position. Inflation is probably pointing at something real about the early universe. It's likely that a genuine burst of expansion really did occur. But we can't say what triggered it. We can't rule out the possibility of endless other universes forming. And we can't fully test its most complete versions. It is, simultaneously, our best answer and an open wound. The flavor of modern cosmology, beyond any single fact, is that these two things, our best answers and our still unhealed wounds, keep becoming the same thing. Notice the pattern forming here. It's the real subject of tonight. Every time we try to nail down another detail of the Big Bang, the theory gives us an answer. But that answer often carries with it a new question, stranger than the one we started with. The cracks don't seem to run out. Behind every crack, we find another one, and we haven't even reached the biggest crack yet. That's the one claiming that roughly 95% of the universe is made of something no one has ever seen. Let me tell you something cold, and I want to say it plainly, without softening it with any explanation. Every star, every planet, every photograph you've ever seen, every atom in your own body, all of it combined makes up only about 5% of the total structure of the universe. The remaining 95% consists of two components, and no one on Earth knows what either of them actually is. Let me show you how we arrived at this staggering claim, because we didn't reach this conclusion lightly. The evidence forced us here. It all began with galaxies spinning faster than expected. In the 1970s, astronomer Vera Rubin, working with her colleague Kent Ford, was carefully measuring how fast stars orbit the centers of galaxies. In her measurements, she found that stars far from a galaxy center were moving just as fast as stars near the center. This directly contradicted classical physics. Think about the planets in our own solar system. Mercury, close to the Sun, completes a fast orbit, while distant Neptune moves slowly. Gravitational pull weakens with distance, so the outer planets should move more slowly. Galaxies should behave the same way. Outer stars should orbit more slowly. But in the galaxies being observed, the outer stars were orbiting at the same speed as the inner ones. It was as though they were feeling a stronger gravitational pull than the visible matter alone could account for. This gave the impression that every galaxy is surrounded by an enormous, invisible ring of mass, one that emits no light, but that certainly exerts gravitational influence. In the 1930s, astronomer Fritz Zwicky had noticed this same phantom mass while studying galaxy clusters. The clusters were moving too fast to stay bound together using only their visible mass. Zwicky called this substance dark matter, though his work was largely overlooked at the time. Rubin's patient, meticulous research made dark matter impossible to ignore, and the evidence that followed only strengthened the case. We found that dark matter bends light, distorting the images of distant galaxies behind it, an effect that can be mapped directly across the sky. In a region called the Bullet Cluster, two galaxy clusters had collided, and the invisible mass passed straight through, separating physically from the observable gas left behind, cleanly splitting dark matter from ordinary matter. We've traced this same evidence into the oldest light in the universe, the pattern in the cosmic microwave background. This pattern only matches our observations in a universe where dark matter outweighs ordinary matter by roughly 5 to 1. From galaxies, to clusters, to the infant universe itself, 6 independent lines of evidence, entirely separate from one another, all point to the same conclusion. Dark matter is real. Its gravitational presence is beyond doubt. And yet what this substance actually is remains a total mystery. For decades, physicists have built extraordinarily sensitive detectors, buried deep underground to shield them from noise, waiting to catch the signal of a single dark matter particle. The result, so far, is nothing. No confirmed detection. And yet we know with certainty that it exists. We've measured its quantity and confirmed that it makes up roughly 27% of the universe. But its identity remains completely hidden, a secret that stubbornly refuses to reveal itself to anyone. Consider how strange this situation is for the world of physics. Imagine a detective who can prove, beyond any doubt, that a particular person was in a room. Footprints in the carpet, the indentation of someone who sat in a chair, warmth still lingering on a seat, 11 independent traces of their presence. And yet this detective can never see that person, never photograph them, never catch them on camera or in any stretch of surveillance footage. For 50 years, using the most sensitive equipment buried deep underground, the search has continued, and the suspect has never once shown their face. That's precisely where we stand with dark matter today. Its existence is beyond argument. Its identity is an absolute blank. Some physicists have begun to wonder whether we've been searching for entirely the wrong kind of suspect. Whether dark matter is some exotic particle we haven't yet imagined, or whether our entire search framework is fundamentally flawed, remains an open question. This uncertainty, and the willingness to reconsider the search itself, is a quiet symptom of a field under real tension. It's worth emphasizing that this invisible material isn't some minor supporting character. It forms the fundamental skeleton of cosmic structure. Without dark matter, galaxies could never have formed in the time available. Gravity would have had to first gather the ordinary gas that makes up the first structures, prevent galaxies from dispersing, and shape the vast cosmic web of filaments and voids that binds all visible matter together. Every glowing part of the universe, every dazzling star, every breathtaking galaxy, takes shape within an invisible, unnamed framework. The brilliant universe hangs like an ornament on a dark, unseen frame. And that's just 27%. A much bigger mystery, dark energy, remains far beyond our grasp, and it's our next focus. But dark matter remains the second greatest mystery. The greatest one arrived in 1998. That year, astronomers measuring distant exploding stars, supernovae, discovered that the expansion of the universe wasn't slowing down. It was speeding up. Everyone had expected gravity to eventually slow this expansion. Instead, the universe is expanding faster and faster. Some force is pulling the universe apart, filling the empty spaces of the cosmos. It makes up roughly 68% of the universe's total content. This unknown entity has been named dark energy. In the Standard Model, referred to as lambda, the cosmological constant, it appears as a fixed energy woven into the fabric of empty space itself. Despite being the single largest component of the entire universe, it remains the least understood. The story of how we discovered it is worth telling, because it's one of the most genuinely shocking findings in the history of science. In the early 1990s, two rival groups of astronomers set out to measure how quickly the expansion of the universe was slowing down. At the time, everyone assumed the expansion had to be decelerating, that gravity, pulling on all the matter in the universe, would apply a gentle brake to the expansion, the way gravity slows a ball thrown into the air. The only real question in cosmologists' minds was whether the universe would eventually halt its expansion entirely and collapse back in on itself, or continue expanding forever, but at an ever-slowing rate. A third possibility wasn't even on the table. To detect this expected slowdown, the teams tracked Type Ia supernovae, stellar explosions that reach a nearly identical peak brightness, making them ideal cosmic mile markers. The difference between their observed brightness and their known true brightness lets astronomers calculate both their distance and, from the redshift of their light, their velocity. In 1998, both groups, working independently, arrived at an astonishing result. The distant supernovae appeared dimmer than expected. The expansion wasn't slowing down. It was speeding up. Some force pulling the universe apart was overpowering the combined gravity of everything within it, and the growth of space itself was accelerating. This unexpected discovery was so shocking that the astronomers spent months double-checking their work, suspecting they'd made some measurement error, before finally accepting the result. Eventually earning a Nobel Prize, this finding left us with a universe dominated by an unexplained force, one that intensifies as cosmic expansion continues. As matter thins out, this force becomes ever more dominant. Dark energy isn't some quiet background detail. It's the factor that will ultimately determine the fate of the universe, pulling galaxies apart at an ever-increasing rate, and eventually dimming the sky itself. It is the most mysterious component surrounding every field of physics. Now imagine the entire universe as a pie, sliced according to what it contains. A large portion of this pie is dark. 68%, more than 2/3, is unexplained dark energy. Another 27% is dark matter, invisible to us entirely. What remains, a thin 5% slice, is filled with light, and it holds the entire visible universe. Every star, every planet, every breathtaking galaxy you've seen in a deep field photograph, every cloud of interstellar gas, the atoms in your hands, the chair you're sitting in, the air you're breathing, the bodies of the people you love, all of it is gathered within this narrow, bright ribbon. Every cosmic structure ever seen through any telescope, throughout the whole of history, is this small sliver of light, drifting in an ocean of two unknowns, dark energy and dark matter. I want you to sit with this fact, not just pass it by as an interesting piece of trivia. Because this is one of the strangest situations science has ever found itself in. It goes beyond mere scientific curiosity, revealing a striking contradiction at the heart of the universe's fundamental structure. Most of reality has gone unnoticed, standing before us like an incomprehensible veil. Everything we think about, everything we care about, is the universe's 5%, the thin bright layer it seems to treat almost like a rounding error, sitting outside its vast dark hole. Let's look at the sharpest edge of this situation. This is the same theory that predicted the early universe's temperature to a sensitivity of 1 part in 1,000. That achievement is undeniable. But it comes with a confession attached. For the equations to work consistently, for the sky to be modeled with this kind of harmony, the theory has to assume that nearly everything in the universe is a placeholder. What we call dark matter and dark energy are, in truth, labels for two enormous gaps in our knowledge. Dark energy. The lambda symbol in the model's name eventually becomes a placeholder dressed up as a Greek letter. It's a confession, wrapped in physics. Hold on to that thought, because we're about to see this placeholder start to move. In this next part, we come to a number the universe refuses to accept. Among all the cracks in the Big Bang, this one is the sharpest, the most precise, and the hardest to explain away. It has accomplished something a good theory's crack should never be able to do. The more closely we've examined it, the worse it's gotten. This crack revolves around a single number. The Hubble constant. The fundamental measure of how fast the universe is expanding right now. In short, it's the current growth rate of all existence. There are two different ways to determine this constant. Both routes should arrive at the same number. But they no longer do. The first route relies on the very early universe. We take the cosmic microwave background, the extraordinarily detailed map produced by the Planck satellite. The precise pattern of warm and cool spots in this light holds all the information needed to calculate how fast the universe should be expanding today. We feed the early universe map into the standard model, turn the mathematical crank, and out comes an estimate for the expansion rate. This estimate comes out to about 67.4 in units of kilometers per second per megaparsec. Don't worry about the units, just hold on to that number, 67.4. From the early universe. Here's an important point. This first route relies on the Planck satellite and the standard model, so you might think the result is only as good as those assumptions. But there's a second, entirely independent early universe method. A massive survey called DESI maps the three-dimensional positions of millions of galaxies and reads the imprint of a sound wave frozen into the way those galaxies are distributed to independently determine the expansion rate. DESI is independent of Planck, and it produces a value of roughly 68.5. A different method, but fundamentally the same answer. So, two independent early universe methods agree that the expansion rate falls between 67 and 68.5. The second route focuses on today, the late universe, our own nearby surroundings. Instead of relying on a calculation from the baby universe, we directly measure the expansion rate. We find stars whose true brightness we know, a special class of pulsating stars called Cepheids, and use them to determine precise distances to nearby galaxies. Then we observe how fast those galaxies are receding. The fact that these two routes no longer point to the same number has become the most challenging problem in cosmology. Both the cosmic microwave background of the early universe and direct measurements of today's galaxies produce conflicting results. This is what's known as the crack surrounding the Hubble constant, the very number that defines the universe's expansion rate, and it's what keeps scientists awake at night, building a distance ladder step by step, each rung calibrated to reach deeper into the expanding universe. A team known as SH0ES has spent years working to make this measurement as flawless as possible. The value they've arrived at is roughly 73. The early universe value falls between 67 and 68.5. The nearby universe value is 73. And the two numbers do not support each other. Now, comparing 73 to 68, you might think the difference sounds small, just a few points. But at this level of precision, that gap represents roughly an 8 to 9% discrepancy, an enormous chasm. Both sides present their results with error bars, ranges of uncertainty, and those ranges don't even come close to overlapping. Physicists express how significant a disagreement is using units called sigma. 5 sigma is the gold standard, the threshold at which a finding is declared not to be a coincidence. The gap between the early universe number and the late universe number has now reached the 5 sigma level. This isn't noise. By the strictest standards in the field, it's real. Here's the part that turns the discomfort colder. For years, it was assumed this discrepancy would eventually disappear. It was thought one side must have made a mistake, some subtle flaw in the distance ladder, or some overlooked detail in the early universe calculation. As measurements improved, it was expected that the two values would converge toward a middle point, resolved the way most disagreements in science are, with better data. That was assumed to be the natural course of events. Better data would settle the argument. But the opposite happened. As the SH0ES team refined the ladder, and as early universe surveys sharpened their maps, the two numbers didn't move closer together. The error bars shrank, but the gap remained. If anything, the disagreement became more pronounced, because as precision increased on both sides, each side grew more confident in its own answer, making it impossible to dismiss the gap as some kind of shared imprecision. Some researchers tried to pin the blame on a single flawed measurement, or a broken rung somewhere in the ladder. These attempts largely failed, because even as individual pieces of the analysis were swapped out and revised, the inconsistency persisted. Consider how strange this is. We built the most precise instruments our species has ever produced. We aimed them at the simplest possible question: how fast is the universe growing? And the better our tools became, the further apart the two answers drifted. This is the exact opposite of the direction progress is supposed to move in. Progress should bring us closer to the truth. Here, progress has pulled two truths apart. Ask the universe how fast it's growing, and its infancy gives one answer, its present gives another, and no matter how carefully we listen, the two refuse to reconcile. It's worth highlighting a structural feature of this disagreement, because this detail is exactly what makes the tension so hard to dismiss. The early universe number isn't a direct measurement of today's expansion rate. It's a prediction. We measure the baby universe, assume the standard model is correct, and run the calculation forward roughly 14 billion years to the present, arriving at what today's expansion rate should be. The late universe number, on the other hand, is a direct measurement made here, now, in the present. No long forward projection required. So the two numbers approach fundamentally the same question through very different routes. On one side, given everything we currently know, we predict the universe's expansion should behave a certain way. On the other, the expansion we actually measure today shows a different value, and the two predictions conflict. This framing offers a hint about where the problem might actually lie. If the early universe prediction and the late universe measurement don't agree, then either there's a subtle error in one of the measurements, one that researchers have searched for and failed to find for years, or, more intriguingly, the assumptions bridging the two are themselves wrong. The bridge connecting the infant universe to the present day, the standard cosmological model itself, may be missing a historical piece. Somewhere between the beginning and now, some event, some component, or some process not currently included in the model may be altering the numerical outcome, reconciling the two values. In other words, the Hubble tension might be less like a measurement error, and more like the universe telling us that our account of its history, from the beginning to the present, is incomplete. If this is the case, this one stubborn number becomes a signpost, pointing towards some new physical phenomenon we still don't understand. You might feel, at this point, like you're going in circles. The more closely we examine everything, the more inconsistent it becomes. Quietly say that thought to yourself. But this isn't only true of the Hubble constant. As we'll see in the parts ahead, this same inconsistency seems to be arising across the entire universe. And a new confirmation is close at hand. A new space telescope called Euclid will map the structure of the universe from a different perspective, and if its main results arrive with the two numbers still failing to meet, it will offer a third, independent perspective. For now, the two numbers hang in the air, refusing to meet. As we move into this next part, it's worth stepping back to see the whole picture, to look at the shape all of this forms together. We've followed the cracks one at a time, tracing them deeper into the problem. But it's easy, in doing so, to lose the thread, to file these away as separate, unrelated issues. A gap at the very beginning. A sky that's too smooth. A patch that raises its own questions. A missing 95%. a number that can't agree with itself. It might be tempting to file all these away separately and move on. But I don't think these problems are separate at all. Stepping back, they form a pattern, and that pattern is the real story here. First, it's worth stating clearly what these problems are not, because this is where most people go wrong. None of the cracks we've examined tonight come from the fringe. None of them are the product of some crackpot theory, some misunderstanding by someone with limited physics knowledge, or some agenda-driven argument. Each one is a real, difficult problem, sitting inside data gathered by the best instruments we have, accepted by the most respected working cosmologists alive today. The cosmological singularity is a theorem proven by Penrose and Hawking. The horizon problem is the very reason physicists developed inflation in the first place. The dark matter and dark energy sector rests on 6 independent, solid lines of evidence. The Hubble tension is measured by teams of scientists across the world, all of whom would very much like to prove each other wrong, and none of whom have managed to. This isn't an attack on cosmology from the outside. It's an honest, self-generated inventory of what cosmology still cannot explain. With that frame in place, look at the shape these problems form together, because they share something in common, and once you notice it, it's impossible to unsee. The Big Bang model delivers an extraordinary success at broad, general scales. It captures the overall expansion of the universe precisely. It accurately predicts the black body spectrum of the relic radiation. It correctly delivers the overall ratios of the light elements. Ask the model a broad question, and you get a startlingly accurate answer. But every time we demand precision, the exact rate of expansion, the true nature of that missing 95%, the precise behavior of the beginning, the fine detail of that smoothness, every crack we found appears exactly at these points. Zoom in, get into the fine detail, and the model begins to come apart in your hands. This is the reverse of how theories usually behave. When a theory is fundamentally correct, better measurements should shrink the inconsistencies. A closer look should turn small disagreements into agreement, and confidence should grow. That's what maturing science looks like. But here, the opposite process is at work. Getting closer produces more inconsistency. Precision, instead of refining the theory, tears at it. The clearer our view becomes, the more the cracks multiply and widen. There's a useful historical example for explaining why this happens. Every theory has a resolution below which it stops being accurate. Above that resolution, it works flawlessly in every measurement, and it always holds true right up until you drop below that threshold, where errors begin to appear. Newton's laws of motion are flawless for building a bridge or throwing a ball, and hold perfectly for as long as you're not measuring speeds near the speed of light, or atomic scale phenomena. In everyday life, Newton is essentially never wrong. At a finer resolution, cracks appear. That doesn't mean Newton was foolish. His theory was simply an approximation, and once measurements grew sharp enough, the flaws in that approximation became visible. The cracks were always there. We simply couldn't see them until our instruments became good enough to reveal them. This points to something we're witnessing in real time with the standard cosmological model. For decades, our measurements were coarse enough that the model looked complete, flawless, and final. Now, we're measuring the universe with such precision that we're dropping below the model's resolution limit into the region where its approximations begin to fray. The Hubble tension, hints about dark energy, early galaxies, and anomalies in the ancient light may all be different masks worn by the same underlying phenomenon, the stitching of an approximation finally becoming visible to eyes sharp enough to see it. If that's true, this crisis isn't a catastrophe. It's a threshold. It's a good theory showing us, through its own small flaws, that a better theory is waiting just beneath it. The second half of this journey points toward exactly where these small flaws are surfacing fastest. Some of the newest instruments we've built have started to call into question the assumption that the largest component of the universe is fixed and unchanging. There's a certain feeling that comes with this realization, and it deserves a name that's neither exaggerated nor understated. This is what's called a paradigm under tension. What's being described here isn't a completely wrong theory, or some lie that needs debunking. It's a framework that has been pushed to the limit of what it can do, a framework that has begun to show, in its finest details, that it's an approximation of something deeper that remains undiscovered. The cracks aren't random. They all seem to whisper the same message. This message is that the current model, built on our extraordinary success, isn't the final word. It contains missing and not so small pieces we still don't fully grasp. We should accept this idea gently, because it charts the direction of our progress, but we shouldn't fully commit to it either, since we're still only halfway there. So far, we've explored cracks that have been known in various forms for years or decades. Now the story turns toward the most recent discoveries, made by the newest instruments pointed at the sky. And rather than closing existing cracks, these new findings are opening new ones. First, the possibility is emerging that the largest, still unexplained component of the universe might be far more than just an unexplained placeholder we've assumed to be constant. We spoke earlier about a placeholder represented by a Greek letter. Dark energy. The lambda symbol in the model's name represents this mysterious energy of empty space. This energy makes up 68% of the universe, and it drives the accelerating expansion. For roughly 25 years, we've had almost no idea what dark energy actually is. But we thought we were certain of one thing, that this energy is constant. The word constant carries more weight than it might sound like it does. The cosmological constant means the same energy density everywhere in space, and the same value at every moment in time. It doesn't grow, and it doesn't shrink. It was the same in the early universe as it is today, and it will remain the same forever. This constancy isn't a minor detail. It's the single assumption the entire Standard Model rests on, which is precisely why the model is called lambda CDM. Lambda symbolizes that constant. If dark energy really is constant, the model holds its shape. We might not know what dark energy is, but at least we'd know it's motionless. But in 2024 and 2025, this assumption began to shake. This tremor was produced by the massive galaxy survey mentioned earlier, DESI, the dark energy spectroscopic instrument. Providing the largest three-dimensional map of the universe ever created, DESI placed tens of millions of galaxies and quasars across billions of years of cosmic history. Its long-range observational power allowed it to track how dark energy behaves over time, comparing its strength in the past to its value today. DESI's second major data release sent a quiet shockwave through the cosmology community. When its map was combined with the cosmic microwave background and supernova measurements, the data fit far better with the assumption that dark energy is not constant, but variable. This finding shakes the foundation of the Standard Model, while also cracking open the door to entirely new avenues of research. When interpreting the data, it's important to be careful and clear, because this result remains genuinely debated, and calls for honesty rather than exaggeration. The trend in the numbers suggests that dark energy may have been slightly stronger in the past, gradually weakening as the universe has aged. Physicists describe dark energy's density using a parameter called W. The current findings suggest that this value crosses a specific threshold, one that simple, stable dark energy models aren't expected to cross. If this transition really occurred, it likely happened a few billion years ago, and it would demand a far more complex, dynamic, and evolving form of dark energy than a simple constant. This energy would no longer be just a fixed parameter, but a structure evolving over time. So how reliable is this inference? The honesty of the underlying evidence matters a great deal here. The statistical strength of this hint ranges, depending on the supernova dataset used, from about 2.8 to 4.2 sigma. Recall the 5 sigma standard threshold for discovery from the Hubble tension. This result hasn't reached that threshold. Still, it's a genuinely intriguing signal, and one currently sparking sharp debate in the literature. Some cosmologists are convinced this is the first real sign of new physics. Others argue this signal may dissolve as the analysis improves. The outcome remains unresolved, and we should hold it with exactly the looseness the evidence demands, neither too tightly nor too loosely. Let me explain why even such a limited hint is enough to keep cosmologists up at night. It touches on something we've already brushed against. If dark energy is weakening over time, this fundamentally changes the future of the universe. It might also quietly ease some of the other inconsistencies we've already identified. Rather than a fixed value, a variable dark energy reshapes the mathematical bridge between the early universe and today in a different way, and that bridge is exactly where the Hubble tension arises. The possibility of this connection suggests that all these problems aren't separate issues at all, but different symptoms of a single missing piece. The mismatch in the expansion rate, the subtle anomalies in the ancient light, and the drift in dark energy all point toward the same underlying gap. This gap may be a feature entirely absent from our current 6-number model. There's no certainty yet about whether this hypothesis is correct. But the possibility that these fractures are connected, that they're all pointing toward a single hidden door, is what makes this one of the most exciting periods in cosmology in a generation. Beneath Dess's results lies an even deeper discomfort, one that goes beyond a single number. A true cosmological constant, whatever it turns out to be, is at least conceptually simple. It remains a fixed property of empty space, requiring no explanation for change. An evolving dark energy, one that was once strong and is now weakening, demands answers to a far more complicated question. What physical process is driving this evolution? What field, what matter, or what new law of nature is gradually changing the strength of the universe's largest component over billions of years? A constant value is a mystery we can set aside. A moving dark energy is a puzzle staring directly at us, demanding an explanation. It's no surprise that even a hint like this is enough to keep cosmologists awake. If the placeholder really is in motion, we haven't just lost a comfortable assumption. We've opened the door to a much more urgent question, one the standard model, as it currently stands, simply cannot answer. But imagine how striking a turn this would be. For 25 years, we couldn't explain dark energy. Still, we could treat it as a fixed, unchanging feature of reality, conceptualized as something we could call a constant. Not understanding it wasn't stopping us. Now, the largest map of the universe ever made is suggesting that this constancy might be an illusion, and that our unexplained placeholder might not be standing still after all. The placeholder, represented by that Greek letter, may well be moving. If this movement is confirmed, what the standard model needs isn't a small patch or a minor correction. It needs an entirely new component, an entirely new kind of physics governing the largest portion of the universe. The constant sitting at the heart of the entire framework, the one that gives the model its name, may no longer be a constant value. The source of this astonishment isn't an outside observer questioning cosmology. It's the most ambitious mapping project in the field, fully accomplishing exactly what it was built to do. Examining the universe more closely than anyone ever has before, this project hasn't found the clarity it was looking for. Instead, it has shaken the largest piece of all. However detailed the map becomes, the thing we were most certain of has become more uncertain. and our newest observational instruments have only just begun their work. In the summer of 2022, humanity turned on the most powerful eye it has ever built and aimed it into the deepest reaches of the past. The James Webb Space Telescope sits nearly 1 million miles from Earth, at a temperature close to absolute zero. When its large golden mirror opened in the darkness, it could see fainter, older, and more distant objects than any instrument before it. Among its many goals, this telescope was designed to observe the very first galaxies, glowing in the universe's youth. Almost immediately, it began sending back unexpected images. Let me walk you through this moment, because it's a genuinely strange experience. The telescope stares for hours at a single patch of dark sky that lesser instruments would consider empty, gathering the faintest streams of light. Photons that left their source more than 13 billion years ago travel, stretched by the expansion of the universe like an infant growing older, before finally striking the mirror and being counted. Then this image is displayed on screens back on Earth. There, in the place where the standard model predicted only small, faint, still assembling galactic fragments, an entirely different kind of object appeared. A bright, large, well-organized galaxy, far more mature and far more massive than its age should allow. The observed universe was only 300 to 500 million years old, a moment in cosmic time occurring right after the beginning, roughly a 48th of the universe's 13.8 billion year lifespan. In this model, structure is supposed to form gradually. Gravity needs time to pull gas into stars, stars into galaxies, and small galaxies into large ones. But the observations showed this process happening far faster than expected. Astronomers, half-jokingly, began calling these objects impossible early galaxies. The brightest and oldest examples earned the nickname universe breakers. A discovery like this is one of those moments that makes you feel the subject is genuinely alive, when you can almost feel the friction between a carefully written timeline and a real-time view of the sky. We built a schedule for how cosmic structure should unfold. Then we built an eye sharp enough to actually observe that unfolding. And that eye showed us a universe moving faster than we'd planned for, reaching a more advanced stage earlier than the schedule predicted. I need to stay faithful to this channel's promise of honesty here, because this story has genuinely softened somewhat since those first images. It would be unfair not to say so. As those first shocking images emerged, careful follow-up work eased some of that initial shock. A review led by a young astronomer, Catherine Kowalski, along with similar researchers, showed that many of these galaxies weren't as massive as they first appeared. Their brightness turned out to come not from an impossible density of stars, but from factors like a rapidly feeding, brightly burning central black hole, or an unusually intense burst of star formation, both of which can make a modest galaxy appear far heavier than it actually is. Accounting for these effects, some of the galaxies once labeled impossible become merely surprising instead, and part of the crisis around the model eases. But there's an important caveat here. The problem hasn't fully gone away. Not every object can be explained this way. Some still pose serious difficulty for the standard timeline, and continue to present surprising findings. In early 2025, a mature, well-organized spiral structure, nicknamed the Big Wheel, was discovered existing far earlier than it should. There's also a group of compact, dense, red objects that Webb has consistently been detecting, nicknamed little red dots, and these remain largely unexplained. Rather than presenting a clear-cut break with the model, the picture is more complicated and more honest than that. When the early universe was first seen in this kind of clarity, it appeared, at least somewhat, out of step with the script. This remains a live subject of debate. Sitting with what these galaxies actually are only deepens the strangeness. When you look at an early object, you're not seeing its current state. You're seeing light that left it more than 13 billion years ago, and has been traveling through space ever since. The galaxy you're seeing is frozen in this image from the universe's infancy. Everything that has happened to it in the roughly 13 billion years since remains invisible to us, still on its way. That light is like a message that could never reach us any other way. So Webb isn't photographing the early universe. It's receiving a message from it, a message that has drifted through cosmic darkness for nearly the entire span of the universe's existence, finally landing on a golden mirror, 1,000,000 miles above a small blue planet, whispering, quietly, we were already here. We had already grown. We were already shining. Far earlier than you thought. The deep impact this kind of surprise has on the model comes from something bigger than expected. The part of cosmology we understand best is the process by which gas turns into stars, and stars turn into galaxies. Over long stretches of time, this process is guided by the most familiar force acting on the dark matter skeleton, gravity. No exotic quantum weirdness, no unexplained dark energy, is required here. Just gravity, patiently gathering objects together. We also have detailed computer simulations of how fast this gathering should happen. So the fact that the real universe assembled its bright, massive, well-organized galaxies faster than these simulations predicted isn't just a minor technical footnote. It challenges our understanding of what we believed was the simplest, most straightforward process of all. Even gravity, even the familiar accumulation of matter, may be following a script we haven't fully read yet. If even this simplest part doesn't fit the script, a quiet, uneasy curiosity arises about how much of the rest actually holds true. This is, in miniature, the essence of tonight. We built our most precise instrument. We aimed it into the deep past. And while waiting for confirmation, we found ourselves facing a new series of questions instead. The closer we got to the beginning, the less coherent the story turned out to be. This isn't a loss of credibility. It's the appearance of a fine, real crack piercing straight through the timeline. To interpret all these cracks together, there's one more place we still need to look. And it's the most sacred piece of evidence for the Big Bang itself, the oldest light in existence. But this light carries a few smudges that shouldn't be there. If there's a single piece of evidence that has convinced the world of the Big Bang model, it's the cosmic microwave background, the CMB. We've touched on this a few times tonight. But now I want to look at it directly, because even the theory's greatest triumph contains a quiet flaw within it. Let's recall what this light actually is. About 380,000 years after the beginning, the universe's temperature dropped low enough to allow the first atoms to form, and at that moment, the universe became transparent. The light drifting through it at that instant was set free forever. As the universe has expanded, that light has stretched with it, and it's still on its journey today, reaching us from every direction as a faint microwave glow. This is, quite literally, the oldest light in existence, a photograph of the universe's infancy, taken when it was younger, relative to its current age, than a single day is to a lifetime. This light shows an almost perfect uniformity. Its temperature matches, at every point, to within about 1 part in 100,000. Its glow matches a perfect black body spectrum, an ideal thermal spectrum, more precisely than anything we've ever measured in a laboratory. When it was first mapped in detail, it looked like a stunning confirmation of everything the theory predicted. Nearly perfect, nearly uniform. But not quite. That not quite is exactly where the strangeness hides. Now lean back for a moment and imagine being able to see this microwave glow directly, wrapped around the entire sky like a shroud. The faint imperfections hidden inside this light, like blemishes in the universe's baby photo, force us to ask new questions. These imperfections unexpectedly contradict the theoretical perfection of the cosmic microwave background, pointing to an incomplete aspect of gravity itself, the very force underpinning the model. What these marks suggest is that we may need to reconsider the universe's history, hinting at the existence of a physical mechanism we haven't yet discovered. So these new findings aren't just a technical deviation. They're also a warning about the foundations of our understanding of the universe's earliest moments. Scientists focusing on these anomalies should be developing new models that reshape our sense of the cosmic microwave background's near-perfect nature. Because this small but consequential irregularity may require reinterpreting the universe's expansion, the distribution of matter, and even the nature of dark matter and dark energy. In this context, future observations and more advanced simulations will illuminate the missing parts of the current theory, and perhaps offer an entirely new cosmological framework. This ancient light, still echoing through the depths of space, has much left to tell us. But this time, part of its voice isn't staying silent. It's calling out to us with new questions. Imagine an environment where a faint temperature wave is felt gently in every direction. Looking more deeply into the largest, broadest patterns within this environment, a series of clues emerge, hidden within the universe's oldest light. First, there's a cold spot positioned in the direction of the constellation Eridanus. This spot marks an unusually large and extremely cold region of the sky. Its size and temperature sit outside what statistical models can comfortably explain. Pure chance isn't entirely impossible, but this strangeness is precisely why it's earned the name the cold spot and become the subject of long-running debate. Second, there's a phenomenon cosmologists have, half-jokingly, named the axis of evil. The two largest scale patterns in the cosmic microwave background, the broadest curves of the hot and cold fluctuations, appear to be aligned with each other. This alone is unexpected. What's more curious is that this alignment appears to sit along the same axis as the plane of our own solar system and our direction of motion through space. This striking coincidence gives the impression that the cosmic microwave background, supposedly the most neutral thing in the universe, has somehow chosen a particular direction, one that seems tied to our own location. The third observation is that the largest scale waves are weaker than the model predicts, leaving the impression that some of the largest structures are quietly missing. Fourth, the two hemispheres of the sky don't fully match. One hemisphere shows slightly more fluctuation than the other. This breaks the assumption that the universe should appear statistically identical in every direction. Now it's worth honestly assessing the strength of these anomalies, because honesty is at the heart of this whole discussion. Each anomaly, on its own, carries a fairly modest statistical significance. Each has some chance of being a random cosmic coin flip or an error stemming from foreground light, our own galaxy's glow, not being perfectly subtracted out. If there were only one of these, most people wouldn't think twice about it. But there isn't just one. First the WMAP satellite, and later the far more precise Planck spacecraft, independently confirmed these irregularities. As measurement techniques improved, these inconsistencies didn't disappear. If anything, they became more distinct. This persistence sits on exactly the same foundation as the pattern we've encountered throughout tonight. Amid all this strangeness, pause for a moment and consider that the entire universe's baby photo, the remnant of creation itself, carries a handful of faint smudges. These smudges aren't randomly scattered. They're gently aligned with the plane along which our own planet moves. This alignment could be a coincidence, explainable as a trick of statistics and foreground contamination, or it could be pointing to the fact that the universe isn't quite as perfect, smooth, and unbiased as theoretically predicted. I don't want you to treat this as a source of fear. I'd rather you feel it as a source of wonder. The privileged dizziness of realizing that the oldest, calmest, most fundamental thing we've ever observed still holds an unsolved secret. Even the crown jewel has a foundation, and that foundation gently, but clearly, points us back home, from the depths of the universe. Let's begin with complete fairness, because this is exactly the kind of anomaly where science can most easily slide from careful caution into looser interpretation. The most likely, mundane explanation is that this alignment isn't the universe reaching out to speak to us directly, but rather the leftover trace of a faint glow, not fully removed from the maps, originating from our own galaxy, or dust within our own solar system. This leftover would appear aligned with local structures, simply because it's an extension of those same local structures. This scenario, put forward by many cosmologists, is a genuine possibility, and it's likely the correct path. But there's still a reason these anomalies remain significant. Even if each individual anomaly is eventually traced back to a mundane explanation, the problem still lies in the pattern formed by all these explanations taken together. One small anomaly, then another, each individually explainable, or dismissible on its own. But together, they form a persistent drip that a supposedly perfect model didn't predict. This is the model claimed to be the most flawless of all. The cosmic microwave background is the domain where the standard cosmological model is at its most triumphant, most precise, and most trusted. But when stubborn, minor features keep demanding explanation within this sacred territory, it's worth remembering that this perfection may always have been somewhat overstated. The smoothness we celebrate may be smooth enough to convince us, while still falling short of reflecting the whole truth. Even in the model's proudest moment, this quiet doubt appears like the last drop of new cracks. Now it's time to look at the oldest cracks standing behind all these new ones, cracks that have existed within the foundation since the very beginning, that have sat there for decades, sometimes patched over, sometimes quietly set aside, but still waiting, because they're part of the same pattern. Among these cracks sits one that's been called the worst prediction in the history of science, and that claim shouldn't be taken lightly. Recall dark energy, the vacuum energy filling the universe and accelerating its expansion. Quantum physics tells us that empty space isn't truly empty at all, that fields are constantly fluctuating, and particles are constantly popping in and out of existence, and this activity carries energy. Physicists used this natural intuition, applying quantum theory to calculate how much energy empty space should contain, then compared this prediction to the actual measured amount of dark energy in the universe. The result: the two numbers are entirely, wildly different. In the most extreme estimates, the discrepancy is measured as a factor of 10 to the 120th power. That's a 1 followed by 120 zeros. It's hard even to describe how catastrophic a mismatch of this scale really is. This doesn't just show the theory is slightly off. The discrepancy is as large as the collapse of the very foundational assumption of what's being measured. Our best theory at small scales, and our most accurate measurement at large scales, produce a disagreement over the energy of empty space more severe than any two numbers in history have ever disagreed with each other. We haven't found a way to fix this discrepancy, so we've quietly accepted it and learned to live with it. This is what's known as the cosmological constant problem, and it has stood, unresolved, beneath the foundations of cosmology for a very long time. To feel the magnitude of this mismatch, let's set aside the exponents for a moment and try a visualization. Imagine estimating the weight of a single grain of sand, and having that estimate come out heavier than the mass of the entire observable universe. Not off by some margin, but so wildly off that the real universe's weight becomes a rounding error next to your estimate. That gives you the flavor of a discrepancy on the order of 120 magnitudes. This isn't a near miss. It's the most staggering quantitative prediction failure in history. And this failure comes from quantum field theory, the very framework that has been tested more rigorously than any other in every other domain of physics. The same physics that can predict certain particle properties to 12 decimal places gets the energy of empty space wrong by a factor containing 120. The strangest part is that the universe appears to have arranged itself to cancel out nearly all of this predicted enormous energy. What we actually observe, that thin, delicate dark energy, is just a small echo of that cancellation. An echo strong enough to accelerate the cosmos, but not so strong that it would have prevented galaxies from ever forming. Otherwise, the universe would have torn itself apart before any galaxy had a chance to exist. Why this cancellation is so nearly perfect, yet still incomplete, remains a mystery. No one has solved it. This problem sits quietly beneath the surface, like a fracture buried under a rock layer that everyone avoids looking at too closely. Now let's look at a second deep crack. This one asks the question of why there's anything here at all. In the hot early universe, energy was constantly converting into matter. The rule is this: when energy transforms into matter, it produces equal amounts of matter and antimatter. A particle and its mirror image, its antiparticle, are always created in pairs. When a matter particle meets its antiparticle counterpart, both are annihilated, converting back into pure energy. So the early universe should have produced exactly equal amounts of matter and antimatter, and all of those pairs should have annihilated, leaving behind nothing but radiation. No atoms, no stars, no planets, and no you. Just pure light and emptiness. Obviously, that didn't happen. Because you're here right now, and this remains the result of a cause we still don't fully understand. The early universe created a tiny imbalance. For roughly every billion antimatter particles, about 1,000,000,001 matter particles were produced. That single extra particle in a billion, an almost impossible surplus, survived the Great Annihilation, while everything else cancelled out. That 1 in a billion remainder is what makes up the entire universe. Every atom in every galaxy is this rounding error. A mistake the early universe left behind for reasons we still don't understand. Why this imbalance exists, why matter slightly outnumbered antimatter along this thin margin, and why anything at all remains instead of pure radiation and nothing else, remains an unsolved problem. The very existence of matter is a subject that demands explanation. The third, and perhaps most mind-bending issue, is this. What makes the universe function the way it does right now? Time flowing forward, the second law of thermodynamics holding true, cosmic history unfolding in a coherent, orderly way, is that the universe's beginning emerged in an extraordinarily special, extraordinarily ordered, extremely low entropy state. How special was this condition? Physicist Roger Penrose, the same scientist behind the singularity theorems, attempted to calculate the odds of the universe randomly landing in a state as ordered as ours. The number he arrived at is too enormous to put into words. The required precision involved a ratio around 10 to the power of 10 to the power of 123. That's not 10 to the 123rd power. It's a number whose exponent is itself raised to yet another exponent. This magnitude is so vast that you couldn't write out all its zeros even if you used every particle in the observable universe as ink. In short, the universe began with such an exquisitely fine-tuned degree of order that no physical explanation for this state has been found. It's simply accepted as an initial condition we have to take as given, and why it's this way is entirely unknown. Even within what's considered one of our greatest achievements, there's a small remaining flaw. This theory predicts the amount of the lightest elements formed in the first few minutes of time. For hydrogen and helium, the predictions match observations with astonishing precision. But for the third lightest element, lithium, the model predicts roughly 3 times the amount we actually find in the oldest stars. This is known as the lithium problem, and despite decades of effort, no shared solution has ever been found. Even within this great triumph of early element formation, the model harbors a gap it cannot explain. I want to specifically highlight this low entropy beginning, because among these other old cracks, it may be the deepest one of all, and it conceals a hidden truth about your own life. The reason time flows forward, the reason you can remember the past but not the future, the reason a cup can shatter but never spontaneously reassemble itself, the reason the universe as a whole has any directionality at all of it traces back to this extraordinarily ordered beginning. Order tends toward disorder. It never reverses. This one-way drift is what forms the arrow of time. But this drift is only possible because order existed in the first place. Had the universe begun in chaos, there would be no drift, no arrow, no flow, and time as we experience it wouldn't exist at all. So your ability to remember this morning, your awareness that your life has a before and an after, the very possibility that events unfold in a particular sequence, all of it depends on the universe having begun in an inexplicably ordered state. The existence of the arrow of time is a debt owed to an initial condition no one can explain. Tonight, as you feel time passing, you're experiencing the outcome of a mystery physics still hasn't solved. Here's what I want you to take away from this part. These old cracks aren't any less important than the new, glittering problems coming from our telescopes. In some ways, they're even bigger because they directly touch on the very possibility of our universe existing at all. Why is there matter instead of nothing? Why does time have a direction? Why isn't empty space carrying 120 orders of magnitude more energy than it does, energy that would have torn the cosmos apart before a single atom ever formed? These questions trace directly back to that inexplicably ordered state at the beginning of the universe. Each of these issues forces us to either accept the confident, tidy explanation the Big Bang offers with real discomfort, tune something with an almost unbelievable degree of precision, add a component we can't even name, or accept an initial condition we can only assume and can never justify. The seemingly seamless foundation we learned about in school was never actually that. It has always been a structure held up by supporting questions still waiting for answers. Usually, we've simply looked past these questions. But tonight, we chose to look directly at them. Having now seen all the cracks, old and new, and having finally perceived the whole wall at once, we've realized it's time to ask what it all means. At this point, I don't want to burden you with a list of problems. My goal is to show you the truth of the foundation and to leave you with the sense that a truly seamless whole never existed. A polished, seamless summary never reflects reality. It's always full of these deep, unanswered questions. The worst prediction in physics. The unexplained existence of matter. The extraordinarily ordered beginning. The missing traces of lithium. These have always been there. Now, standing where we can see both the oldest cracks and the newest ones at the same time, we're in a position to ask the ultimate question. What does all of this actually mean? I promise you the answer will be different from what either side, shouting the loudest, tends to claim. At the end of this long walk, we're looking back over the whole picture. We're talking about a theory with a hole right at its starting point, where the equations dissolve into infinity. An extraordinarily smooth and flat universe, patched by an inflation we haven't detected, perhaps even one that can't be tested. 95% of the universe made of two components no one can even name, one of which may not be the constant we assumed it was. A single fundamental number split into two answers that refuse to come together. Galaxies growing far faster than expected, pointed out to us like smudges on a photograph. And underneath all of this, the old cracks in the foundation are still there. The worst prediction in physics, and a beginning too orderly to have arisen by chance. The question we've been circling all night has finally matured. What does it mean that the more closely we examine the Big Bang, the less sense it seems to make? First, let me clarify what it doesn't mean, because two loud camps will interpret this in opposite directions, and both of them are wrong. This doesn't mean the Big Bang has been debunked. When Webb sent back those early galaxies, corners of the internet lit up with claims that the Big Bang was a lie and had finally been overturned. That claim is false, and everything you've seen tonight shows exactly why it's false. Nothing we've discussed tonight shakes the fundamental claim that the universe was once hot and dense and is still expanding. That claim rests on the redshift of distant galaxies, the existence and spectrum of the cosmic microwave background, and the abundance of the light elements, and it remains one of the most solid foundations in all of science. Every crack we've found appears in the fine details, in the precise version of the theory, not in the foundation itself. Those declaring the Big Bang dead have confused tension in the model's fine structure with a collapse of its core. At the same time, it's worth stressing that this doesn't mean everything is perfect either. These aren't small, tidy puzzles that clever minds will soon file away and solve. The belief that the standard model is the final word looks unshakably solid, because the patterns we see are so remarkably consistent and directional. But these cracks aren't shrinking. Some are widening, and that widening becomes more apparent as our perception sharpens, which is the exact opposite of how a finished, complete theory should behave. So if this model has neither been disproven nor completed, what does it represent? The reframing that the evidence, in my view, points toward is this: it's a perspective that's both quieter and stranger, and, in a way, far more exciting than either of the two extremes. The foundation of the Big Bang, a hot, dense universe expanding over time, remains solid. That isn't the source of the fracturing. Where the fracturing actually happens is in a subtler assumption. In the quiet belief we've carried inside our successes, that a model built from 6 numbers should be able to explain absolutely everything, at every level of scrutiny we could ever apply. For a long time, this assumption went untested, because our measuring instruments weren't sensitive enough. During that era, the model looked like an extraordinary approximation, but at the resolution we could actually observe, that approximation was indistinguishable from reality itself. Now, for the first time, we've built instruments precise enough to see past that approximation. The Hubble tension, the hints of shifting dark energy, the early galaxies, and the smudges on the ancient light, they're showing us the texture of exactly where the approximation runs out, and where something deeper begins to emerge. Making less sense doesn't mean the universe has become irrational. It means that despite the full power of our current story, it's still only a draft. Earlier in this video, I told you to hold on to the phrase "first draft." That phrase now carries a different meaning. It once described a caricature, a point suddenly exploding, an image that never reflected reality. Now it points toward something far broader. The entire Standard Model, the 6 numbers, the constant lambda, cold dark matter, and inflation itself, is a first draft. A truly remarkable draft, one that can predict the universe to within less than 1% accuracy. But a draft nonetheless. A draft this good isn't a failure. It's a promise. It's a promise of how extraordinary the next draft is going to be. Listen to what the cracks are actually doing. The more closely we look, the less internal consistency the model shows. The first time we encountered this phrase, discussing the Hubble tension, it produced a sense of alarm. Now, we should hear it in a different voice. A theory that quietly contradicts itself right at the edge of our sharpest measurements isn't dying. This is precisely the signature of a new field of physics waiting to be found. Every contradiction functions like a finger pointing toward the place where new physics is hiding. The Hubble tension tells us something about the expansion isn't understood. Shifting dark energy tells us a new component has joined the largest part of the universe. Early galaxies tell us structure is being shaped by rules we haven't fully written down yet. These aren't the sounds of science collapsing. They're signs that science stands right at the threshold of its next great idea. Feeling the draft filtering through the cracks is as close as it gets to feeling the next one arrive. This has happened before. Newton's law of gravity was a magnificent first draft, ruling the sky for 200 years. But over time, tiny cracks appeared. A slight wobble observed in Mercury's orbit pointed to a place where this first draft fell short. It's not accurate to say that cracks in physics destroy the foundations of science. Quite the opposite, these fractures opened the door for Einstein, leading us to a picture where the fabric of space-time itself curves to describe gravity. This new view was a far deeper, stranger, and more elegant truth than Newton's original vision. The cracks in the old framework of atomic physics didn't end science either. They gave rise to quantum mechanics. Every time our most powerful theory begins to contradict itself at its own edges, it means we're standing right at the door of a deeper theory. Contradiction points toward a new door. We shouldn't forget that today we're in a far more advantageous position than before. Back then, a single subtle anomaly in Mercury's orbit was one lone crack in the old physics. The single mind who noticed that one shortfall, Einstein, found an entire new world hidden inside it. We now have not just one crack, but many at once, all offering overlapping clues, pulling us toward drawing new maps. This might feel, at first, like things are getting worse. But flip the perspective, and more cracks simply mean more clues. The growing number of independent anomalies places tighter constraints on what the deeper theory must ultimately look like. Arrows pointing from many different directions toward the same hidden truth show that the universe is being generous with us. It isn't hoarding the answer. It's handing us the pieces of the puzzle, one after another. The Hubble tension, the dark sector, early universe galaxies, and the ancient light, these are all pieces of this larger puzzle. How these pieces eventually fit together will shape the cosmology of the future. We may not yet have the insight needed to assemble them, but we're holding more pieces on the table, at once, than at any point before. I connect this idea to the ordinary experience of living, and of curiosity itself. It's tempting to imagine that all the great revolutions in understanding happened safely in the past, that the heroic age of discovery is behind us, and only details remain. But what I want to tell you tonight is that this belief is entirely mistaken. We're still living inside an unfinished story. The textbook narrative of our origins, printed with so much confidence, is right now, quietly, being rewritten in real time by telescopes and instant surveys peering into the darkness. The next Einstein may already be alive. The idea that will resolve the Hubble tension, explain the dark sector, or unlock the mystery of the singularity may be taking shape in someone's mind right now, or waiting for a mind not yet born, and you're living through the chapter that comes just before that answer. This is the sharpest the questions have ever been, the most open the mystery has ever felt, and you could think of this as the most romantic chapter of the entire story. So as you drift here in the dark, I don't want you to feel fear. I want you to feel privileged instead. Because right now, at this exact moment, a paradigm sits visibly under tension, its cracks laid bare, with no one yet knowing what will grow from them, and that is one of the rarest, most exciting positions a curious mind can ever occupy. The people living in the years just before relativity, just before quantum mechanics, stood in that same place. They quietly sensed a picture, thought complete, silently coming apart at the seams. They stood at the threshold of a revolution they had no name for yet. We're standing in that same narrow, charged gap tonight. We're in the middle of a transition from one story of the universe to the next. This is exactly where the next cosmology will take root. So the next time you hear someone say the more we study the Big Bang, the less sense it makes, I want you to hear that sentence the way I hear it. It isn't the sound of a theory failing, or the universe behaving like something broken. It's closer to describing a reality that resembles nothing we've tried to compare it to before, boundless and strange. The vast whole is whispering to us, in the only language it has, through missing numbers, missing components, and a beginning we still can't fully write down, that our first draft was only ever a draft. It's pointing toward the fact that the real story, the one not yet written, will turn out to be far more astonishing than anything we currently believe. The claim that the universe is becoming steadily less senseless is, in fact, mistaken. Quietly, patiently, It's preparing to reveal a deeper meaning that lies beyond our current knowledge, and in this preparation, we get to stay awake in the dark and witness the exact moment of that transformation unfold. And with that, let your own thoughts do the same thing the universe is doing right now. Not collapsing, not falling apart, just gently loosening their grip, drifting a little further from the sharp edges of the day, settling into the wide, unfinished dark, where nothing needs to be solved tonight. Somewhere out past the edge of what any telescope can see, the next answer is quietly taking shape. And here, in this small, safe, well-lit sliver of the universe, in your 5%, made of ordinary matter and warm breath and slowing thoughts, there is nothing left for you to do but rest. Let the cracks stay open. Let the questions stay unanswered. Let the universe keep drafting its next chapter without you. And let yourself gently drift off to sleep,